Welcome back to ECE 320A. Obviously, there's some excitement in the room. There might be some excitement on another location on campus a little bit later, but I'm glad to see all of your faces today. You're not skipping out early. Announcements, homeworks 1 and 2 are available on mastering, and those are due on the 13th and the 20th, and our exam is, and I think those days are Sundays, and the exam is on a Thursday, the 24th of September, exam number 1. Today, what I want to do is work some examples. The first one is, how do we deal with a network of loads? How do we compute the complex power, and how can we use that information to find or obtain other useful information? Then we'll look a little bit more at the power triangle. I hope that you are becoming comfortable with that. That's what I want you to be doing, is feeling very comfortable with P, Q, and S and how those pieces fit together. And we'll look at then working with the components of complex power after reviewing a little bit more on the power triangle. And then we will maybe get to the last topic or goal, which is working with phasors. And in that sense, you need to realize that it's not just numbers or magnitudes. It's a number or a magnitude and an angle. And you can't just add the magnitudes. You have to add these voltages and currents vectorially. They go together head to tail, or tail to head, then tail to head, etc. And you can't just be computing or adding up magnitudes. Here's the problem that I want to begin with. I cheated and already wrote it down, so I'll talk a little bit as you're maybe writing this down. Hopefully you can see that there are 3 different loads in this example, and those loads are not all interconnected in the same way. You have load 1 going, let's say, in series with the other 2, and the other 2 loads are actually in parallel. We are told what the voltage is that's supplying this network of loads, and it's given in RMS units. It's 100, and we've decided to just say there is where we have our time t equals 0. We're going to assume that the voltage is our reference angle, the source voltage. That's 0 degrees. And then we have different component parts specified or given to us relative to the different loads. And concerning load 2 and load 3, since they do have some reactive power, we need to know either the sign of that reactive power or be informed whether that reactive power is inductive or capacitive. And that's what I mean by IND and CAP. Load 2 is an inductive load. Load 3 is a capacitive load. I'm assuming you are quicker than I am at sketching that. What I want to do now is actually find, and now I'm calling it something else. Let me go ahead and change that just a little bit, because I think I'm going to call that I sub S, and I'm just saying it's an RMS unit. If the voltage is in RMS, we talked about that last time. What I want to do is find that current that's being supplied by the source. And as you are looking at this problem, you might either virtually or explicitly start sketching these triangles so that you see a relationship on how much real power is being absorbed by the different loads, how much reactive power, and in what direction. In load 1, what kind of a triangle do we have there? That's just a line, isn't it? That is a triangle that really hasn't expanded in the vertical direction. Load 2, we're going up or positive, and in load 3, we're going down as far as our angles are concerned. The Q is positive in load 2, and it's negative in load 3. What we are really doing, or what I want to make clear on this example, is it really doesn't matter how these powers are, or how these loads are interconnected relative to how we compute the total power. We can now simply look at all of that and say, let me combine these powers. The real powers are horizontal. Let me add those up algebraically. Let me algebraically add up the vertical or the reactive components. And the net of all of those will be the total complex power for those 3 loads. And it doesn't matter that load 1 is in series with the other 2, which are in parallel. Unlike in voltage and current, it obviously matters how they're interconnected, how the voltages are measured across the elements and how the currents are going through the elements. Let's then look at the solution to this, or one way of doing this would actually be just setting it up in a table and keeping track of all of the different pieces and the parts. Or I'm going to add like components, and by that I'm meaning add up the P's, add up the Q's, and then the S is complex, so you can't just add magnitudes of S's, but add up like components of the complex powers. For example, let's just create this table. We have 3 different loads. We have the power in watts for each of those loads. We have the reactive power in VARs for each of those. And we have the complex power in volt amperes of all of those. And we could also talk about the apparent power, also in volt amperes, which is just the absolute value of the complex power. In load 1, we had 0 VARs and 100 watts. The complex number then, S sub 1, is just 100. And the magnitude of 100 is 100. That's the easy load. Load number 2 is now 700. And they said it was inductive for the reactive component. The real component was 200. And now what's the sign on Q sub 2 if it's inductive? That has to be positive. So now we could say that explicitly, and now we have for S sub 2, 200 plus J, 700. And if you find the absolute value of that complex number, it ends up being a little bit more than 700. It's 727, which is just the hypotenuse of that right triangle. 200 squared plus 700 squared added up together, take the square root, and hopefully you get 727. Load 3 is 300 watts for the real power. It's 1500 VARs for the reactive piece or component, and that's capacitive. That then has a minus sign, and we now have S sub 3 is 300 minus J 1500. Again, you take the hypotenuse of that triangle associated with 300 and 1500, and you end up with a number a little bit more than 1500, which is 1530. Questions on that? Yes? Did everyone hear the question? Where did these signs on Q come from? I think that was the question. I just rephrased it a little bit, but if we now have load 2, I assigned 700 to be a positive number, and in load 3, I assigned a negative sign to 1500. What did we talk about last time? I hope we talked about that relative to determining the sign of these Q's. Pardon? Eli and ice help determine what each one is. In this particular case, Eli, it's an inductive load. And so if we now have Eli on this guy, the current lags the voltage. And so theta sub V minus theta sub I, if the angle on the current is less than the angle on the voltage, which it is if the current is lagging the voltage, then theta sub V minus theta sub I is positive, and that's giving us our positive Q. Similarly, if this is capacitive, there's the ice. The I now, what I'm trying to say is we're looking at this theta sub V minus theta sub I in both of these cases to determine, let's say, theta sub 2 and theta sub 3. We're not computing those yet. We could from trig, but the angle associated with load 2 is now going to be a positive angle because theta sub V is bigger than theta sub I. In load 3, I is bigger than theta sub V, so theta sub 3 is negative. Does that help? That's where these signs, SIGN, come from on the Q's. And now if we want to determine the totals, we can simply sum the columns. We have, and luckily I've made the powers easy to sum, 1, 2, and 3, which is 600. 600 watts total. Then we need to take 1500 from 700, which is now minus 800, and the total complex power, we can either add up vectorially the 600 and the minus 800. We know 800 and 600 are orthogonal. The real power is horizontal, the reactive power is the vertical. And in this case, what kind of a load do we have? In aggregate, if we look at all three of these loads as one big load, demand from our source, what does it look like? Is it real? Is it inductive? Or is it more capacitive? So it has a flavor. It's capacitive. It looks more capacitive than inductive since it's a negative Q. What I want to drive home is, and one of the points, is if we now look at the total apparent power, that's simply the magnitude of 600 minus J800. And that luckily is sort of this 3, 4, 5 triangle, ending up with 1,000. That is the apparent power that the aggregate of those three loads are presenting to the source. And what I want you to see is that that is definitely not the same as adding up the three individual apparent powers. That's not equal to 100 plus 727 plus 1530, which, if you do the math, I hope it's 2,357. The apparent powers don't add. You have to add up the components vectorially and then find the magnitude of the total to obtain the apparent power seen by the source. Are we finished? No, we're not even started, are we? Really? Darn. We want I sub s. I sub s is up here on the left, and we've just found essentially, effectively, what's inside that yellow highlighted region as a whole. We now know the total load presented to that source of 100 volts. But we can use that now to our advantage. We are looking for the source current kind of frightening in this building, isn't it? I think we're right underneath the flight path. Now what? Yes. So now this apparent power is, the question was, do we need to say that that's dissipated? In effect, yes, but the reactive piece, it really isn't a dissipated power, but it is a demand. So you could say there's an apparent demand of 1,000 volt amperes. That's maybe, I wouldn't necessarily say that you have to say that this is absorbed or supplied, but you could put units on it. It's now 1,000 volt amperes. Is that okay? You could say that the load is demanding 600 watts. This apparent, the reactive component is capacitive, so now this whole thing looks like a big capacitor to your source. Yes. So your source is having to actually produce enough power to support minus 8,000 var, minus 800 vars. It has to deliver that to the load. Now what do we do? If we're looking for I sub s, we've really lumped all of this into a big blob, which is now this S sub t, and that was 600 minus J 800 volt amps. And we know that this, in RMS units, was 100 at 0, and we're trying to find that current. Now we just use our relationship for voltage and current in phasor form relative to complex power. We know that the complex power being demanded of us is this V I sub S star. And we were given V as a phasor. We computed the total power being demanded. The only thing that's unknown is the current. And that current actually has two parts or two components. It's a complex number. It's a phasor, which is why we have the, well, that's why we have the bars over them, and that's why the conjugate makes sense. We can actually take the conjugate of a complex number. We now have I sub S bar star is equal to ST over V. And that's now 600 minus J800 over 100 at an angle of 0 degrees. Now, if you have a calculator that handles complex math, you can just plug that in. If you don't, maybe you want to do another step and you're doing a division, which it's easier to divide when all of your complex numbers are in polar form. You could convert that rectangular numerator into polar form. We know the magnitude is 1,000. The angle is 600 and 800 in this direction. And we could, via trigonometry, and maybe I should say minus 800, that's now minus 800 over 600, and what do you end up with for that? The inverse tangent of that is now this minus 53.1 degrees, which makes sense. It should be bigger than 45 since the vertical part is larger than the horizontal part. That's why I like drawing triangles, because if I do something wrong entering it in on my calculator, I maybe have a check on my work. This is pretty easy to divide, 1,000 divided by 100, and the angles aren't too bad since one of those is already 0. Question?
Yeah, so on an exam, if you have a calculator that's complex,
Oh, what kind of a mood am I in? The question was, can we use a calculator on the exam? I'm not going to police calculators. If you've spent $200 on a calculator, you can use it to its full potential. I'm not going to go around and make sure that you can't or certain things. So what you might do though, if it looks a little like, I usually suggest that maybe you put something here and say from calculator, do an arrow somewhere, and then I'll go, where in the world did he end up with 25 at an angle of 37 from this? And you've said from calculator, and I go, hopefully it's just a punch-in error and not a conceptual error. Is that clear? Yes. So the question is, will the exam be multiple choice? I don't know. How many students do we have here? Maybe I'll change my philosophy, but it's probably going to be more long answer, okay, and not circle a bubble. You may want to circle your answer and make sure that it's legible and that it's clean. If I'm trying to grade all of these exams and it's difficult to follow, then I start getting ornery. And you don't want me to get ornery, okay, when I'm grading. Where were we? Trying to find the current that is being asked of this source, and we have to keep track of the fact that it's the conjugate of that current that we've just computed. That's now this 10 at an angle of minus 53.1 degrees. And that's in amps. And the units on that are consistent with what we started with the voltage, which we're in RMS. This is now an RMS unit. And we use that fact there. We indirectly were assuming that those phasors were in RMS units. If they weren't, then we would have had a 1/2 V bar I bar star if they were in maximum values. Now, it should be, I hope, clear that all we have to do is change the sign of that current's angle to obtain the current of the source. And our voltage that we started with was 100 at 0 degrees. And if you were just given that current and that voltage, could you say anything about the type of the load? Now, you have maybe 3 answers, right? It could be purely resistive. I just feel like walking around. And if I see something good on the tabletop and if I'm hungry, it may get consumed. I usually don't supply. No, I don't care. Just be careful with your food. That's not what I mean. But we're talking about consuming and supplying, right? So that's where that came from. We have power consumption of these loads, and we have the voltage sources or the sources supplying. Now we want to know what kind of a load it is. It could be purely resistive, it could be somewhat inductive, or it could be somewhat capacitive. Relative to these expressions, is it resistive? And on the exam, if you can't seem to think, you might just say it's not resistive because 53 is not equal to 0. At least you're telling me you've got something there in terms of understanding of what we're talking about. What can we say? We could go back to Eli and Ice, couldn't we? Suppose that somebody says, well, what's the power factor? I don't know, let me just pull a formula out of the air and see if it makes sense. But we could look at the power factor. The power factor is the cosine of the angle of the load, the effective load, which is now the cosine of theta sub v minus theta sub I. I'm just sort of playing right now. I'm just playing with formulas. You could also say here is our total impedance, which is V bar over I, what did I call that? Sub S bar. And if this was a magnitude of V at an angle of theta sub V, and this was a magnitude of I at an angle of theta sub I, then this is the magnitude of Z at an angle of theta sub V minus theta sub I, where this is our angle. Using that notation, what do we know about the power factor? We have theta sub V was 0. Theta sub I was 53. So theta is now minus 53 degrees. That's the angle of our load. We now have minus 53.1 degrees. If we take the cosine of that, the angle disappears. I'm sorry, the sine disappears. This is now 0.6, but how can we use that angle or that sine to fill in the second piece of our power factor expression? It's now looking more and more like a capacitor, isn't it? It's leading. And we could have maybe seen that up here if we said Eli and ice. We realized that the angle of our current is leading the angle of our voltage. The current is leading our voltage, so we had a capacitive system, net. And we could have seen that also back here when we found our total power had a reactive component of minus 800 VARs. Question? Eli and ice. Eli the Iceman, this is just V is equal to L di dt, and I is equal to C dV dt, and it just is conveniently arranged so that I in the inductor is after or lagging the voltage, since it occurs later in that three-letter sequence, and ice, the voltage is behind or lagging the current, so we say the current is leading the voltage in ice. We're always referring to lagging and leading via the current, or the current is being the reference. Did that help answer Eli and ice? Eli's getting rich off of that ice business. Oh, sorry. Now, suppose that I wanted you to, now we are effectively finished with the first piece of that. We said find I sub s. But now if you were reading ahead, maybe you were already getting anxious when you saw that I sub 3 over there on the right. Oh, that's part B. Part B is find I sub 3. On an exam, you might have Z parts, A, B, C, D. And if you miss part A, you don't have a clue about, or never mind. Then I only have to grade part A. See? You want multiple choice? You guys heard it. No. I just lost the class. How would one find I sub 3 in RMS? And if you are having trouble figuring it out, I would start delaying your answer by maybe making another sketch and thinking through as you're sketching. We have S2, we have S3, those are complex numbers. We have S1, that's also complex. It doesn't have a non-zero reactive piece or component, but it's still complex. We have V, we have I of the source, and we have this current that we're trying to find. What do we do now? Current divider. So how do we work a current divider in a circuit, in just generically? How does a current divider work? We need the impedances of the two elements that current is being divided among, correct? Do we have the impedance? I'm hearing yes and no. I'm confused. What do we have? We have power, and the power is not the same as impedance. And we weren't given the impedance, were we? I could have started by here's load 1 and it looks like this inductor and this resistor. Here's load 2, it looks like this inductor and this resistor, etc. Yes?
Why IRMS? We use S equals IRMS squared.
If we have the current, so we have this current, let me see if I can paraphrase the question, or maybe that was more of an answer, wasn't it? Not a question. That's the same current, isn't it? So it is begging us maybe to try this current divider, but we don't have impedances. If we knew a voltage, then we could find the impedance, because we know Ohm's law is still true in phasor form, but we don't know the voltage across those two parallel loads because some voltage is dropped across load 1, isn't it? Roughly, if you just looked at these relative magnitudes, if you were really in a pinch, you could, in an interview, and you go, I haven't a clue where to even start, you could say, you know, hypothetically, what if we just neglected load 1 just to kind of think about this? You know, you're leading this interviewer on. You're showing them how much you know. You say, suppose load 1 didn't exist or it was 0. Then the voltage of 100 volts would slide right across, and that's what you would have on those two loads, wouldn't it? And you know the current feeding those two. You could now start to maybe make a little bit more sense, but let's view this from another perspective. Circling all 3 was nice. What if we circle 2? If we circled 2 and just focused on load 2 and load 3, now what do we know? We know the current feeding those. We could find the total I don't know what I want to call that, a intermediate total power complex of load 2 and load 3. We know this, we could find this voltage drop. They're in parallel, aren't they? If we now knew, let me call this V sub L, and what I'm trying to say is if we could take this and find this total power of load 2 and load 3, then we could do something similar to what we did in the overall picture before. Except now we're going further into the problem, and all we really need to know now would be these two loads that are in parallel, their total power. So how do we find that? I'm calling that S sub 2, 3. That's just the vector sum, or the complex sum of the second load's power and the third load's power. And you've already computed those, or were given those. This was 200 plus J 700. And S3 was 300 minus J 1500. We now know that S sub 2, 3 is 500 minus J 800 volt amperes. And these A's and B's are all A's and B's of part B. Maybe I shouldn't have used A and B. Hopefully that's not confusing. Now we can find this voltage across those two loads. Because effectively you have a complex load, S sub 2, 3, being supplied by a current, I sub S, and that combination of those two have the same voltage across them. In this case, we have S sub 2, 3 is equal to V sub L, I sub S star. Or V sub L is now S sub 2, 3 over I sub S bar star, and this is 500 minus J 800 over whatever this was, 10 at minus 53.1 degrees. Converting that rectangular complex number to polar form, it's 943 at an angle of minus 58 degrees. And we now find that this voltage across those two loads is now 94.3 at an angle of, well, if I get rid of that point, makes it easier, roughly, approximately, minus 58 minus a minus 53, minus 5 degrees. Does that seem reasonable, that number? You had a 50-50 chance, right, on that one, yes or no? Now you're going back to multiple choice, right? No. So this is a voltage that's less than the source, which seems to make sense. You're dropping some voltage across that purely resistive transmission line to those next two loads. So you would expect this voltage to be less than the 100 that was supplying it, and it is. And in this case, this voltage is lagging or behind the other voltage, isn't it? Now, we wanted to find I sub 3. How are we going to do that? Now we can use that same equation. Boy, you're going to have this equation memorized, aren't you? Now on exam 1, you're going to say complex power, complex power, complex power. I better change up the questions, huh? So now I sub 3 is S3 is equal to V sub L I sub 3 star. And now we know S sub 3, we know V sub L. We can solve for the conjugate of I sub 3. S sub 3 was 300 minus J 1500. V sub L was 94.3 at an angle of minus 5. This was now 15. Wow, I'm really getting into the significant digits. 1529.71 at an angle of minus 78.69 degrees, all over 94.3 at an angle of minus 5, leaving us with 16.22 at an angle of minus 73.69 degrees. That's the conjugate of the current going through the third load. We can find the actual current by changing the sign of that angle, and we end up with I sub 3 being 16.22 at an angle of 73.69 degrees. And that's amps RMS. That seem okay? Math seemed to be reasonable. There's I sub 3 has a magnitude of 16. What was the source current's magnitude? 10. Where did that rabbit come from? Somebody just do some magic. What's happening here? We started with 10 amps in, and somehow we ended up with 16. Pardon? Is I sub 2 negative? So now what's going on? This is now, remember, that was the magnitude of this current. And what do we have up here? Boy, I better quit going back and forth. We have an inductive load coupled with a capacitive load, and those are actually sharing or exchanging currents amongst themselves, and it's not having to come directly from the source. So they're playing catch like we talked about before, and they're helping each other out in terms of the current demand that they are requesting be supplied to them. So, in a sense, this is what we will start to do if somebody had a big industrial load and it looked very inductive in behavior. We might hang some capacitors on that, and then we will require less current from the power company because we are making up or allowing, we're sort of supplying these reactive VARs that our industrial plant is needing by having this capacitor. When we want to get rid of them, instead of throwing them all the way back to the source, we just throw them locally to that capacitor bank, and then it throws them back. So this is not necessarily unexpected that we have a source current that is in magnitude less than one of the load current's magnitudes. Okay? Questions on that? Let's then look at, as somewhat of a review, I think we talked about this a fair amount last time, so maybe I don't want to spend too much time on this now, but the power triangle. I want you to be very comfortable in relating different power components or going back and forth or being able to find unknowns from what you're given. And here, I'm sure you're interested in how everyone performed on that learning styles quiz. Maybe you didn't all answer it accurately, but in terms of visual and verbal, 90% of the class was visual versus verbal. Does that surprise anyone? No. So when I say that you're maybe visual, that's what I'm meaning. But we need to learn how to do these things verbally too, because I may give you a word problem. Okay? We'll do that in a minute. Here we have a picture. There's S. Here's Q and here's P. And there's our angle of the power, theta, which is theta sub V minus theta sub I. And in expressions, we have S is equal to P plus JQ. Power factor is the cosine of theta, and P, if you wanted to, is now the apparent power, or the magnitude of the complex power, times the cosine of theta, or times the power factor. So with these pictures and with these expressions, I want you to be, if you're given a couple of those, I want you to be able to find the others, because it's helpful to be able to have P and Q so that you can add and subtract those vectorially or component-wise. So that now if you wanted the power factor, that's just the real power over the apparent power. Do you see why the power company wants that to be, or maybe you as a company want that to be close to 1? You want most of the apparent power that the power company is supplying you to be consumed in your plant. You want P to be almost as big as the magnitude of S, or you want that angle to be small. The power company will probably charge you a surcharge if that power factor gets small. Let's say the power factor is 0.8. Maybe they'll tack on a surcharge because they're having to supply you with the voltage and the current demanded of your load, but you're not using maybe as much as what they apparently are supplying you for. And Q, this then is P over V and I with the appropriate voltage and current. Q, if you wanted that, or if you were given that, you know it's related to the angle and the apparent power, where the sine of theta we have already defined as a reactive factor. We won't really use that too much, that terminology. And if you were given the angle theta, or if you had Q and P, you could then find theta. Theta is now the inverse tangent of Q over P. And if we have a positive theta, or a negative theta, that tells us what type of load you are being presented with. If it's positive, what do you have? Inductive. Or the terminology in terms of how the current is related to the voltage, it's a lagging, and that's coming from Eli. If it's negative, then your load is looking more capacitive. The current is leading the voltage, and that's coming to us, or you can interpret that in terms of ice. And that's how you can use this power triangle to help you in your analysis when presented with a problem. You can have all sorts of these pieces given to you, or maybe not very many of those pieces, but you can infer a lot by backing out or extracting the information you need from this picture and from these formulas. So let's look at an example. Suppose somebody gives us load 1 is 100 kVA, power factor is 0.8, and it's lagging. Load number 1. Load number 2, let's say we are told it's 50 kilowatts, power factor of 0.9, and it's leading. And maybe that's being supplied those two loads through a source voltage of 200 volts at 0 degrees, and the units on that are RMS. And maybe we don't know the current. Yet. Now, there's two parts to this problem. I've given you all the information, and now you're asked to find A, the total complex power, oh, let me rephrase that. I may phrase this a lot. I'm sorry if you're taking notes in pen. Find the total complex load power. We have two loads, so that's all of those loads. And B is find the current supplying the loads. And that current is I sub S. Is it clear what we're wanting to do? And now this is just playing with geometry. What I want you to be comfortable with is, or I hope you're not confused by the different units on these powers. We can't just add 150. Is that clear? They do not have the same units. What are we given in load number 1? Do you see a picture of what you're given? Are you starting to form images of these loads mentally? And if you're not, maybe you just should start drawing them if you're not seeing them. What should you see with load number 1? Horizontal, vertical, hypotenuse, angle, direction of the angle. Do you see any of that? You see a hypotenuse. I hope no one's listening to this lecture. We see a hypotenuse. We see an angle. Which direction is that angle? Up or down? Up. So the hypotenuse is going up. We're going uphill. Do you see that for load 1? So load 1 and maybe we don't know what 0.8 corresponds to in terms of an angle, but it's lagging, so we know it's going up. But if you did the inverse cosine of 0.8, you would know exactly what that angle was. But now I'm dashing what we don't yet know. We do not yet know P1 or Q1. And really, we don't know theta 1 explicitly. But we were given the hypotenuse, S1, and that was 100 kVA. That was an apparent power. We were also given a power factor, so let's find the angle. That's the inverse cosine of 0.8, or the power factor is the cosine of theta. We're finding theta 1. This is now about 37 degrees. And what can we put in terms of the sine on that angle? That's positive because we were told that the current was lagging the voltage, and theta sub 1 is theta sub v minus theta sub I. And if the current is lagging the voltage, then just assign some positive number or value for theta sub v and 0 to theta sub I, and we have a positive angle. Is that okay? So the current lags the voltage. Now we have all we need to compute P1. That's S1 cosine theta 1, and Q1, which is the magnitude of S1 sine of theta 1. This is 100K times the power factor, which was 0.8. That's 80 kilowatts. And Q1, sine of 36 is 0.6. This is now 60 kilovars. Questions on that? We now have that first load and all of the information related to its power triangle. Again, what we're trying to do is find the total complex power. We need all of these pieces in order to add them up component-wise to obtain the total complex power. Now what are we seeing in load 2? Are you seeing a hypotenuse, a horizontal line, a vertical line, or both, or all of the above? Horizontal. Now we're seeing real power, which is horizontal. We have a power factor of 0.9. What's the direction of that angle? Down. It's negative because it's leading. We now have then, for load 2, we see horizontal and a down angle. We have P sub 2. What we don't have is the hypotenuse and the reactive component. P2 is 50 kilowatts. Theta sub 2, inverse cosine of 0.9. What's the sign of that going to be? It's going to be negative, right? Because it was a leading power factor. And in ice, the current angle is leading. This is now minus in degrees, 25.8 degrees. We know two values in that expression. We don't know the apparent power, but we can now solve for it by taking P sub 2 and dividing by the power factor of load 2, or the cosine of theta 2. The apparent power then of load 2 is 50K divided by 0.9, or 55.6 kVA. And now Q sub 2 is that numerical value for the apparent power of load 2 times the sine of theta sub 2. When we found both of those, we now have 55.6 K times the sine of minus 25.8 degrees. And now the sign does keep track of the SIGN of the angle in its argument, and Q sub 2 becomes minus 24.2 kilobars. Now we have all of the pieces that we need to compute the total complex load power. S1 was 80K plus J 60K. S2 was 50K minus J 24.2K, or 130K plus J 35.8K volt amperes, or we could put that into polar form and we could find the apparent power of the two loads. And that's roughly 135 kVA at an angle of 15.4 degrees. Questions on that? Now we can find, I think part B was part B, to find the current supplying the loads. And we know the voltage across those. Now we need to apply our complex power formula again. That's just V I sub S star. We'll find then the complex conjugate of the current supplying those two loads. And because we found those, or the polar form of that, now that's now handy to plug it into this quotient relationship. And I'm going to just get rid of the conjugate now and change the sign in my final answer. I now have 674 at an angle of minus 15.4 degrees amps RMS. What's the aggregate load look like? So the current leads the voltage, is that what I heard? What was the voltage that was supplying this? 0 degrees. The current supplying it is negative. So if our theta is theta V minus theta sub I, is theta sub I smaller or bigger than theta sub V? Smaller, isn't it? Or behind. The voltage angle is sitting at 0, and the current angle is sitting there, and we're always spinning counterclockwise. So if you were standing right here and you were looking, I don't know, that was supposed to be, man, that's why I'm not into art. How's that? So now you're looking at that point, which waveform are you going to see first? The voltage. The current is lagging, it's behind. So the load current lags the voltage. Is that clear? Questions on that example? Yes?
When you're finding the total complex power, why is it not 100K plus 50K?
The question was, I think,
55K, not that. The 100K right there.
okay, there's 100 kVA, which is what? That's load 1's apparent power. That's the magnitude of the hypotenuse. And now you're saying load 1.
Oh no, I understand. It's because it's the apparent.
So we can't add magnitudes, can we? We can't just add the lengths. It's essentially like in a triangle, two of those sides, if you just took the sum of those two sides, it's always going to be more than the third side. So in this case, we need to add these guys vectorially. We have 80 and whatever it was for Q2 minus 24, and then 50 and 80 to get the total. Any other questions on that example? Now, yes? I don't know, I just grabbed it. So now theta, or 0.6, what was theta? Theta 1 was 37, 36.8. If you take the sine of that angle, this is now this 0.6, 0.8 relationship between that angle. So the 0.6 I just quickly wrote down because I knew that was the sine of 36.9 degrees. Other questions? We have 30 more minutes. Let's keep going. Game starts in about 6 hours. Now, I was in a conversation with one of the deans about this class, and I started saying, or the dean was saying, maybe I shouldn't identify which one, but they were asking, why do your students need 320 if they've already had 220? And I said, because I'm teaching 320. He didn't like that answer. Then I proceeded to say something like sinusoidal steady state. And he goes, sinusoidal is not steady state. I said, okay. He said, it's sinusoidally time varying. I go, yes, but the transients have all died out. And we like to play with sinusoidal conditions, and it's convention that we call it steady state. Are we clear with that? When I say sinusoidal steady state, what that means is the transients have all decayed, and we're just looking at all of these signals in the circuit or in our system. They're all shaking at the same frequency. And in the United States, what's that frequency? And this is not 60 hertz, is it? 60 hertz is 60 times a second. I can't shake that fast. Okay? You can't see that if it was off and on that fast. Now, what was I going to say? Something about the game and 30 minutes, 6 hours. We are going to start back up with this, but what I want you to think about over the long weekend is the fact that now that we are dealing with sinusoids we have to keep track of these voltages and currents vectorially. We can't just add magnitudes. So keep that in mind as you're working these problems. Enjoy your long weekend. I'll see you on Tuesday.